Alright, welcome to another video on shear force and bending moment diagrams. In this video we're going to be talking about triangular distributed loads, and essentially we're going to apply the same technique of analysis that we used in the previous videos. So the first thing we need to know is that the shear force as a function of the displacement or the distance from one of the ends that we choose is going to be equal to minus the integral of the distributed load x dx. Now the reason we need to place that minus at the front is because the force is essentially always pushing downwards. If it was going up, then we would just change the sign. But in general, when you put things on something, it's just the weight acting downwards on it. So essentially we just denote it by a negative sign. The next thing that we're going to do is we're going to define the bending moment as the integral of the shear force. And in that case, we don't need to add any negative signs, it just stays the same. Now for the actual distributed load, in this case we have a triangular distributed load, so we know that the area of that is going to give us the resultant force, which is going to act at the center of this area, but we only need to calculate the x coordinate. So this is going to be located at 1/3 from this side. The resultant force Fr is going to be equal to the area of the triangle, which is in this case 3 times 10 divided by 2. So that's just going to be 15 kilonewtons. And this is going to be acting at 1/3 from the right hand side. So essentially the distance from here to there is going to be 2 times 10 divided by 3, or 20 on 3. And then this other distance here is just going to be 10 divided by 3. Alright, so now that we have that, we can draw a simple free body diagram. So we're going to place our resultant force over here, which is 15 kilonewtons, and it is going to be located at 20 divided by 3 meters from the left hand side. Here we're going to have two reactions, reaction A in the y direction, but the reaction horizontal is going to be 0 because there are no external reactions here that are horizontal, and then over here just the reaction, let's call it RB. And we know that the total distance between those 2 points is going to be 10 meters. And this is going to allow us to solve for those reactions. So first of all, we can take the sum of the moments about point A, which should be equal to 0. Now let's assume clockwise is the positive direction. Now we're going to have minus 10 RB. So this is going to be rotating in that direction. And now this one is going to be plus 20 on 3 times 15. So that means we're going to have 0 minus 10 RB plus 15 divided by 3 is 5 times 20, that's 100. And now that means that RB is going to be equal to 10 kilonewtons. And then the next thing is going to be, we're going to do the sum of the forces in the y direction. But you can already figure out that it's just going to be 5 kilonewtons for this one, because those two need to add up to 15 kilonewtons. So in this case, we just have RA plus RB minus 15. Now we know this is 10, so that's going to be RA is equal to 5 kilonewtons. And that's the answer for that reaction. Now the next thing we want to do is, since this is a triangular distributed load, then that means that the distributed load itself is going to have, it's going to be a linear equation. So the first thing we need to do here is find out what that linear equation is. So essentially we can assume that this point over here is just the origin of a set of axes, and I'm going to draw them in a different color so you can see that more clearly. So suppose this is the x-axis, and this one over here is the y-axis, and this is just the origin. This is essentially just a straight line that is passing through the origin, so the y-intercept is 0. And then the next thing is, well, we know that the total height over here is 3, and then the total extension is 10, so the gradient is going to be 3 on 10 times x, and the y-intercept is 0, so that's essentially our function. So now to calculate the shear force, in this case we're just going to have the integral, and it is going to be negative, of this function. So it's rise over run for the gradient, x dx. integrate that, that becomes minus 3 on 20 x squared plus some constant over here, let's call it v naught. But we know that v naught is going to correspond to this because at this very point here, the internal shear force is going to be equal to the reaction at A. So we know that this is going to be equal to 5 kilonewtons. So essentially this function is going to become 320 x squared plus 5. And now the next thing we're going to do is we're going to calculate the bending moment equation by simply integrating the shear force with respect to x, and that's going to give us the following. So we're going to have minus 1 over 20, so the 3 is going to be divided by the 3 here, x cubed plus 5x plus some constant mo, but we know that in this case that's going to be 0 because the moment reaction here is 0, there's no moment reaction. So this is going to be our equation for m, minus 1 on 20, x cubed plus 5x. Okay, so now we have all that. We can start by essentially just drawing those things. So start by the shear force diagram. That's V in kilonewtons, and then x in meters. And here we have the origin. Now to begin with, we know that we're going to go up by 5 kilonewtons. That's a point load. So we're going to start at 5. And that makes sense because even if you look at these functions, you know, well, if you plug in x equals 0, you're going to start off at 5. Now the next thing we're going to notice that this is essentially pushing down on it, but there's more force on the right hand side than there is on the left hand side. So in essence, we could try and calculate where the maximum is going to be. So in order to do that, what we do is we differentiate this function. So that's just going to be 3 on 10. So that's going to be 3 on 10, actually minus 3 on 10, x plus nothing. So in this case, we know that the maximum is just going to occur at the origin. And that's not unexpected because if you look at the equation here, that's just a parabola that is centered at the origin. Well, it is not centered at origin, but it is going to be symmetric about that. Now the next thing we want to find out is, well, what is going to be the value, say, at 10? Well, the value at x equals 10 is going to be minus 10. So that means that we're going to go down to minus 10, and that's going to be over here. So that's at 10 meters. So essentially the function is going to look like this. So it's a concave down parabola. And now we notice, well, we should be back at the origin, right? Because this is essentially the end of that beam. So where is that shear force coming from? But then we notice, oh, we have another reaction here that is 10 kilonewtons and it is going up. So that means that we're just going to go straight up by 10 kilonewtons. And that's how we end up back at the origin. So in this case, we're going to have these two areas. So they're going to be parabolic in shape. Now, if we wanted to figure out this point where they intersect, we essentially need to find the roots of this equation. So we set v equals 0, then minus 3 on 20 x squared plus 5. So one thing we can do is we can multiply everything by 20. So we get 0 minus 3x squared plus 100. And then we can pretty much just multiply both sides by negative, and then we have x squared equals to 100 divided by 3, which implies that x is going to be equal to the square root of this. So 100 divided by 3, which is about 5.7735 meters. Okay, so that's going to be the point at which it crosses the x-axis. And as you can tell, we would not have been able to guess that because it doesn't happen that you're going to have this point crossing the x-axis wherever you have the resultant force. It never is the case. I think that's only the case when you have a perfectly symmetric loading, like a uniform distributed load or so on. But in general, that does not happen. So we shouldn't expect it to cross it at exactly the same point. Now for the bending moment diagram, we're going to do the same, but we're going to plot the function of the bending moment. So we have x and m as a function of kilonewtons times meters. That's the origin. Now for this one, we know we're going to start at 0 because if you plug in 0, that's essentially what's going to be. Then we know, okay, so this is going to be negative. It is a cubic equation, so that means that it is actually going to go up, but it is going to be going up in a sort of a weird fashion. So in this case, we're going to look at this function and we're going to say, okay, so this is positive, so that means we're going to go up by a positive value. Now, where is the maximum going to occur? Well, it turns out that the maximum on the bending moment diagram, since we have the relationship m equals integral of v dx, then what is actually going to happen is that if we take the derivative of this to find out the turning points, then we get the function for the shear force. And it turns out that the function of the shear force, that is 0, is going to correspond to this equation over here. So essentially, the maximum bending moment should occur at this very point here where we have the 5.7735. And then that means that we're going to have a curve that is essentially just going up like this. And that's going to be, if we calculate basically by plugging into this formula here for the bending moment, that should have a value of around 23.87 kilonewtons meters. Oh, actually, my bad, I miscalculated that. This value should actually be 19.25. And then what's going to happen is we're going to go down because this is a negative area, which means that we're going to go back over here. So essentially at 10 meters, we should have 0. So let's plug that into our calculators to see if we get that. And indeed we do. So we actually go back to 0 straight away. So we're going to have a negative kind of curve. Let me redraw that. And that's our bending moment diagram over there, with the maximum bending moment occurring at this point over here. And in the next video, we're going to do more examples and we're going to look at more complicated distributed loads.